back to the channel, everybody. I hope you're all doing well. It's kind of a dreary Saturday here, rainy and cold. Hopefully you got some good weather. Hopefully you can work on your car, whether you got bad weather or good. Hopefully you're not doing it out in the rain. So today we're going to talk about something that is probably a little controversial, and I don't necessarily mean to stir the pot, but we're going to talk about the subject, do VE numbers actually matter in the VE table? So you've been looking at probably one of my favorite Ferrari engines. This is the F2002 Tipo V10 F1 motor. So Formula One motors are, as most of us appreciate, the pinnacle of motorsports as far as naturally aspirated specific output. They're always fairly small. This was a 3-liter that I think in 2005 was reputed to make 1,000 brake horsepower because it would turn, 20,000 RPM, something ridiculous. The V12s went that higher. They were a little bit larger engines. The 2.4 V8s, all high revving engines. We may have discussed those in the torque management series last year. I can't quite recall 100%. But why are we looking at those? Because they actually represent, from a mechanical engineering standpoint, one of the highest volumetric efficiency produced engines that exists. They're somewhere between 125 and 130%, which means that basically they run in boost because of how efficient they are, because of everything being tuned in the airbox. And even though they're in A, they're pulling in more air than the displacement would dictate. When you look at a book like Fundamentals of Internal Combustion, it's been calculated, and I don't personally know how accurate this is. I trust the source, but the maximum VE anything could ever achieve is 138%. And that is a representation of displacement versus the amount of air that it can move. It has nothing to do with boost. The engine is an air pump. So if you have a 3-liter engine and you move 125%, well, that means that you're going to have another 750 cc's of air going through that engine per cycle. That's what that represents in the short version of the explanation. So we're going to look at a couple of sources online, just real quick. Then we're going to look at some actual examples of how this plays out in a standalone. And then I'm going to tell you what I think, and you can draw your own conclusion. Because I don't feel that there's necessarily a right answer or wrong answer, and we're going to get into that at the end of the video. So let's go to the first source and kind of see what we're reading to establish what I just said. This one's really simple. Just Google it, because you can get Race Car Engineering. You can actually get f1technical.net. So we're going straight to the source as reported by people that have access to the info. Developing over 300 horsepower per liter and boasting a volumetric efficiency of 125% at 20,000 RPM, they, meaning Formula One engines, produce more power for their capacity than any other normally aspirated 4-stroke engine anywhere. And then if you look, you can kind of see in that F1 Technical title there that I'm not going to click on. It says that if it was 2.4, an efficiency of 1 would mean 150 times 2.4 liters is 360 liters per second. The article claims 150 liters per second. 450 divided by 360 is 125. So, establishing some of the math. Okay. That's normally aspirated. Typically, we deal with turbo engines. The numbers are whatever the numbers are for naturally aspirated, right? So, if I put 15 pounds of boost in, does that mean that my volumetric efficiency has gone up 100% because now I've doubled the pressure on the motor? Well, let's go to the next reference. In this case, it just so happens to be Haltech. And I'm not going to read the whole thing, but I'm going to read the first paragraph, and you can go find this. It's on their page under tuning with VE, volumetric efficiency. The first paragraph says, what we are most interested in is the mass of the air, and that's because mass is affected by temperature and pressure. This isn't really a problem. We can control it. We measure air temperature with the intake air temperature sensor and pressure with a MAP sensor. So running 15 or 30 or 60 pounds of boost does not double, triple, or quadruple our engine efficiency. How could it? Now, when we move down here, we're going to cover a few things that you want to stop and think about and maybe draw on a piece of paper, whatever works for you. But the third paragraph says, early on we stated that VE varies with RPM and engine load, and the fuel map axes are based on these two variables precisely because they change the VE. Isn't that directly contradicting? While on the surface it may sound contradictory, it actually isn't. That's because boost alone does not change VE. To understand that, let's look at where the boost comes from. I'm going to jump up a paragraph to number 2, and I did these out of order on purpose. Our air pump didn't get more efficient at pumping air from intake to exhaust by adding air into the intake at a higher pressure. Our air pump is equally efficient under boost. We simply make more power because the higher air mass in the same air volume. We are no more efficient at moving it from one point to another, i.e. in and out. The turbo becomes a restriction on its own, both on the inlet side and the turbine side. Those are my words, not theirs. So we've established that the engine is its own air pump. We could hook up a hose, as we can imagine, and you can actually find videos of how they tested things in the early 80s with giant air tanks. You can feed an engine pressure at any boost or any RPM or boost level that you want. The engine doesn't know that it's necessarily under pressure because the valve is still open and closed. Open and closed. It can only fill so fast. And it's going to get a slight boost because the piston has a pressure differential, but it evens out because in the end you're still letting out high pressure air. So realistically, that efficiency stays a fixed number. Now, let's look at some data from a real world application as the car came in and as the car left. It's one we've already talked about. It was the 1JZ VVT car from Fuel versus VVT. And I'm going to go over some stuff starting with the injector data because there's a lot of emphasis put on injector data being the only thing that truly matters. So let's start with that and we'll kind of talk about some of the details. So this is the injector scaling table. Also happens to be versus injector pressure differential, which we talked about in the custom table episode. You see at 43.5 psi, it says 1345. That's what it's flowing in cc's per minute on gasoline. Now, it just so happens we thought that that car had an issue, so we took the injectors out, flowed them on our flow test, and we saw 1340 cc's. Okay, so the injector data, very accurate. The latency data was as provided from the manufacturer of the injector. Now, when we switch to the VE table, it's going to become very apparent that something's not adding up. Please keep in mind that this car did not actually have any fuel system problems. But in order to meet its target air fuel numbers, these are the values we're seeing. So it spools about 4,000, 5,000 RPM. We're already 125%, 127, 29, 130, 133. Now, as we move out, this car was running about 28 pounds of boost at one point, 7,500 RPM. We're 129% efficiency. Does it seem reasonable, based on what we've covered for Formula One engines, that this one, at more than half the RPM, is just as efficient as the pinnacle of motorsports? Well, of course not. So why did the numbers end up where they ended up? One reason is the injector flow data is based on gasoline, and most injectors are flowed using heptane. So the argument is, oh, well, nobody burns heptane on the street. Very true. But a lot of the math that we see is based around specific gravity. So let's jump to that real quick. So up there in the corner, we're going to see 737.2 kilograms per cubic meter is the density. That's gasoline, ethanol free, I believe, or possibly isooctane. I might be wrong about that, but at any rate, that's what fuel density for 0% gasoline is. We don't have consistent mixed ethanol, let alone truly consistent zero ethanol fuel. So one thing that we can determine is that number is based on set pressure and set fuel temp. So our fuel model is based mostly around that number. Fuel density changes as the fuel gets hotter, colder, it's under more or less pressure. So realistically, we need to do a custom table specifically for the primary fuel density to cover everything that we're going to work with. To be fair in this test, that's not often done. And I'm not pointing fingers at anybody. Maybe some people do this, maybe some people don't. You're only going to add certain amounts of details to your fuel model based on the software that you have, your ability to alter that software. Maybe you can make a custom map for it, maybe you can't. I'm going to hit F3 because I actually don't know. Oh, I got 2 axes. I can do a lot. So I can do both of those. I can do fuel temp and fuel comp, and that's actually 2 axes that it had pre-listed. So you and I both learned that at exactly the same time. That's pretty cool that Haltech gives us that ability to be as accurate with the fuel model as possible. I am assuming there are other manufacturers that do the same. So now we're going to switch to how this ended up during our test. You guys have seen the VE table for the most part, at least at the low RPM and where I hadn't really gotten into boost. So I'm going to show you the injector data, and then I'm going to show you the finished VE table and let you decide what really is the most important. So let's do that. So I've switched maps, and I just wanted to start on this page so you can see that I realistically started the same spot, primary fuel density being gasoline. This is a flex fuel car, but Haltech's map by default includes this value, 737.2. So we're starting off in the same spot, even though now I can see that, hey, I have the capability of fixing this exactly how I need to in the future. So we have that. We're going to go to the injector flow rate. So before we had seen 43.5 was 1345 cc. So in getting my numbers right on gasoline, what I found is the number was closer to 1250. So that got the VE numbers actually fairly similar at idle and cruise. I did play with the injector latency, the injector dead time a little bit. I like to do that versus fuel pressure and voltage, so I kind of come up with my own little table. A lot of people have varying options and opinions. I've done it versus ethanol content actually also. As we started adding ethanol in, I noticed that I had to start trimming the table in addition to what the flex fuel model was doing. So you can see that by the time I got to E70, E75, I had to tell the injector it was significantly smaller. That's an example of that specific gravity number changing. Probably also the fuel temp. Few things there that were affecting where the scaling number came in. And like I told you, I literally just learned that when you learned that. For what it's worth, it is 4:22 p.m. Saturday, the 7th of January, 2023. So we're learning together. It's kind of cool. Now, when we go to the VE, you saw some of this before down here. This happens to be the 30-degree advance, which is pretty easy because we can see this nasty spot down here, the hole in the fuel map. But when we get to peak torque, or not peak torque, but during spool, we see our numbers are not 133% like they were. Now we're 103, 105, like for just a split second. Then it drops back down. It holds 100 for quite a while and then starts to taper to 93 out the top. So what I consider to be more realistic numbers. So who's right and who's wrong? Everybody. Because you also need to keep in mind that you have to do what is going to work for you in the situation. We have race cars and we have street cars, and none of them are perfect. We have fuel system issues that we can't account for. Things like the fuel line size might be wrong. The fuel filter flow might not be right. We might not have enough voltage at our fuel pump. We may have to correct for things. At some point, we get the car tuned and decide to change the cams, and none of these numbers are going to work. Or we learn something new. Maybe today you learned about doing fuel versus intake cam target, which, by the way, unfortunately, we can't do in the Infinity. Well, not to this level of precision anyway. We could do it versus fuel trim on the main fuel trim map. I haven't tried it. I'm pretty sure we can do it. I guess I should say that. So that being said, even some of these numbers aren't 100% where they needed to be because I didn't apply all the trims to them. But out the top, all my fuel map ended up looking like this. Where earlier in an episode, you saw that it was all blanked out at 100, and I said, hey, all you have to do is look at the trim, subtract the trim from 100, and you're pretty close. So that's the fast button I have found. So I did that for the most part, and maybe this is off by 1%, but whatever, it's closed loop, it's fast, it's going to work. So we have all those variables contributing to the number that maybe you see some tuners, and good tuners, and I'm not calling them out. I'm not saying they're doing anything wrong. These numbers might be 140 on a good fuel system because they want their injector data to be 100% accurate. And maybe for how they do their torque modeling, they need the injector flow number more than the total number in milliseconds. I don't know how their fuel models work. I'd have to look at it. So there's possibilities for why they do it the way they do it. For most of us, the mortals, you can make it look normal. It doesn't have to be 140% because we're not doing an OE level torque request like we would in a Bosch Motorsport ECU or some Motec applications like the Lamborghini Audi or GTR, where those numbers need to work the way they need to work, so that if you say I want you to make 1,000 Newton meters, you make 1,000 Newton meters. We'll have an episode coming up where I show you the Ford fuel model from a Bosch ECU that is renowned for being simplistic, but it's amazing how accurate their predicted torque value is based on fuel flow. So it will work. And I didn't quite finish the point, but if you look at this map, you can put a 200 in there. Haltech knows that these numbers, by and large, are imaginary because we're not OE level engineers, and you're not going to have the ability to retune your car all the time for changes. So, or on a dyno at least, maybe you have to do it at the track. So the shortcut is add 20%. So they gave you the range to do that until you figured out how you're going to correct for it on a dyno, if that's your choice, if you have access to it. So we know none of these motors are going to run 200%. We know that that isn't going to be physically possible. We've already covered that. But in the end, whether it's real or imaginary, there are ways that I prefer to do it that maybe some others don't. And so this is an example of what I think is a good looking fuel map, only because it does pretty much follow what you would expect to see. It might be a little low and a little high depending on the cam position, but it's pretty close to reality. We'll switch to some of the other cam positions here in a second. This particular example, peak power is 6,800 RPM typically. maybe 7,000 on some of the poles, but we can see the cam timing at 6,500 right here. 6 degrees, 7,000 is 0. If it was holding 100% to target, which very few cars ever do, that'd be what, 3 degrees to 0 degrees. So when we switch to the base fuel tables right there, now we're a realistic 95.8% VE instead of 125, 126. 6,500 is 97.2. A little bit more realistic to me. That's how I prefer to do it. You can see that the numbers leading in towards peak torque, where we're probably 25 degrees, right in the 100 range, 100 and a half. As it's coming out, still right in the 100 or so. 30 degrees seem to have the biggest gain right here. That's my method for doing it. Yours may vary. Other world-class tuners, and I'm not putting myself in their category, I should say world-class tuners elsewhere may do it completely different. I just choose to do it this way because I like my numbers to look more like a real number based on engineering. But again, we talked about it. It could be based on their fuel model, something advanced in there that they are doing or not doing for their torque management. I don't happen to know. Obviously, we learned today we can revise ours based on fuel temperature and composition to get the specific gravity number even more accurate. So in the end, no. VE numbers are just a tool like anything else. Thanks, guys. This was kind of a long one, but I appreciate you sticking in there and listening to me babble about it. Hopefully you were able to take something away. If this is content that you like, please feel free to hit the thumbs up button. If you or your friends or car group that you might be in might be interested in this, subscribe, share, do what you can to promote the channel. I appreciate it. I thank you for watching. Take care.